All right, so we're in section 4.3 now. We're talking about spanning sets. Um, so, to motivate the idea of a spanning set, it's useful to look at something that happens a lot in different areas of higher mathematics, and that's this concept called decomposition. So, oftentimes in various branches of math, algebra, analysis, topology, things like that, we like to take a certain class of mathematical objects and look at a way to break them down into some combination of simpler objects from that class. So it's very vague, but I think a good example, a good accessible example is something that we call the fundamental theorem of arithmetic. Now, you may not have heard of this theorem if you haven't taken a course in number theory, but you have actually used it in previous math classes, going as far back as even pre-algebra. The fundamental theorem of arithmetic is a theorem concerning positive integers and the prime numbers. So basically what the fundamental theorem of arithmetic says is that you can take any positive integer greater than 1 and represent it in a unique way as a product of prime numbers. And we usually call that prime decomposition or something to that effect. So take, for example, the number 120. We can break this down into a product of prime numbers. 2 to the third power, so 2 times 2 times 2 times 3 times 5. The fundamental theorem of arithmetic is what guarantees that this decomposes into a product of prime numbers, but not only that, it says that this is a unique decomposition. It says that there's no other set of prime numbers that also multiply to 120, not counting rearrangements of the same numbers we have here. So in this sense, the prime numbers are the simplest version of the integer, or the simplest subset of the integers, in the sense that they only have two divisors, one in themselves. And numbers like 120, composite numbers, are more complicated because they have more factors. That's hopefully an accessible example, but again, the idea is taking an object in the class of positive integers greater than 1 and breaking them down into products of simpler objects, prime numbers. So we do this all over the place in math, and in linear algebra, it shows up in the form of what we call spanning sets, or span. So how do we relate this concept to vectors in vector spaces? Because that's where we are right now. We've talked already about linear combinations, and we've done it in a couple of different contexts. We've talked about linear combinations of matrices. We've also talked about linear combinations of just general vectors. And the idea here is going to be to take a vector space which usually has an infinite number of vectors in it. All of the vector spaces we've looked at, except for the 0 vector space, have had an infinite number of vectors. So that's generally the case. But we want to find a way to pick out a finite subset of a vector space such that all of the other vectors in that space can be reconstructed from that finite set by forming different linear combinations of those. So to give you an example of what I mean, let's take a look at the vector space R3. R3 we know has an infinite number of vectors in it. They look like the set of all ordered triples of real numbers. But we've shown that taking those things that we call the standard basis vectors, I, J, and K, any vector in R3 can be represented as a linear combination of those three vectors. AI plus BJ plus CK is equal to the vector ABC. What that means is that in R3, despite the fact that there's an infinite number of vectors present in that vector space, we really only need 3, and then the ability to create linear combinations of those to reconstruct the other infinity of vectors in that space. So we can kind of reduce this vector space down to a set of just 3 vectors from which all others can be built. That's the idea of the thing that we call span. So the set IJK, I would call this a spanning set for the set for the vector space R3, because all of R3 can be built from this set using linear combinations. To make this a little bit more precise, let's give some definitions. So if V is any vector space, and if every vector in V can be written as a linear combination of the vectors in some set S equals V1, V2, all the way through Vn, then we'll say that S spans V. So we're going to use the term span in two different senses, but they're related. One is a verb, one is a noun. So here's the verb version. And to say that a set spans V is to say that all possible linear combinations of the vectors in that set will give us all of the vectors in V. Okay. Now on to the noun. If S is equal to that same set, V1 through Vn, we're going to say that's any set of vectors of some vector space V, then the set of all linear combinations of vectors S is called the span of S. And we use this notation. We just say span, and then we write the set next to that. Okay, so again, this thing right here represents a set. And it's the set of all linear combinations of these n vectors here. Even though this set is finite, the span of this set will usually be infinite because there tends to be an infinite number of distinct linear combinations we can form out of this. All right. So let's start with the first theorem, really important theorem. Let's let S just be this set of vectors, W1 through WR, where these vectors are chosen from some vector space V. We get two results pretty much right away. The span of that vector space turns out to be a subspace of V. Now, again, I want to come back up here. A subtle distinction that you might need to make between these two, and maybe I should have used a different labels for these two vectors because these can actually be doing different things here. Remember, to say that this set spans V, put a different way, that's the same thing as saying that the span of this set is V. But not every set of vectors will span the vector space they come from. For example, if I come back up here to this example, if I threw out the vector k and looked at the span of the set ij, well, the span of that set would not include every vector in R3. The fact that k is missing means that we would actually only be getting the xy plane if we looked at the span of those two vectors ij. But the span of the two vectors ij is still a subspace of R3, even though it doesn't span all of R3. So coming down here, that would be true of any set of vectors that I could choose. I could choose them completely randomly, and if I took the span of those vectors, it always generates a subspace of the vector space V that they came from. B, having established that that's a subspace, the span of those vectors turns out to be the smallest subspace of V containing those exact vectors. So for example, if you have let's say a vector space, let's coming back up here to this example, if we look at the span of just one vector I, that'd be the set of all linear combinations of that one vector, which if you only have one vector really looks like the set of all scalar multiples of that vector. In that case, we'd be looking at the x-axis. If we're talking about R3, that'd be the x-axis in R3. But there's other subspaces that contain that x-axis. Many different planes will pass through the x-axis or contain the x-axis. So, sorry, that's my dog. The span of this set is a subspace, but there are other subspaces of R3 that contain this one vector, that contain I, and they would the span of I would have to be the smallest subspace that contains this one vector. Okay, and what do we mean by smallest? Well, smallest in the sense that any other subspace W that contains those R vectors will also contain the entire span of those R vectors. Okay, so that makes the span of those vectors a subset, or a subspace, if you will, of this larger subspace W. Okay, so let's prove this. Starting with part A, we need to show that something is a subspace of a vector space V, and that's where we have our subspace test. Remember, we need two things. One, we need to know that the vector space is the set is non-empty, and two, we need to know that it has closure under both operations. So first of all, this proof actually leaves out the verification that it's non-empty, so I should include that, but I'll do that part verbally. Is the span of this finite set of vectors non-empty? Well, we're assuming that the set itself is not empty. So if I form a linear combination of these R vectors, let's say 0w1 plus 0w2 plus, putting zeros in front of each one of them, then the sum of those would just be the 0 vector. So this contains, at the very least, the 0 vector. Okay. Now beyond that, do we have closure under both operations? Well, if u and v belong to the span of this set of vectors, then what that literally means is that both u and v can be written as linear combinations of these R vectors. So I could say that u is equal to c1w1 plus c2w2 and so on. V is equal to k1w1, k2w2 and so on for scalars, c's and k's there. There exist those scalars that would give us this by assumption here. So to prove that this set is closed under addition, I want to show that u plus v also would have to belong to the span. But what is u plus v? Well, we've proven enough properties of vector spaces here, and even just the vector space axioms, to know that adding vectors together, we can do something similar to combining like terms. If I have c1w1 plus k1w1, the scalar in front of the w1 is going to look like c1 plus k1. I'm combining like terms, essentially. And if I did that for each of these like terms, then u plus v is equal to c1 plus k1w1 plus c2 plus k2w2 and so on and so forth. But you notice this is a linear combination of the vectors w1 through wr because these are just scalars in their own right. So that means u plus 1 belongs to the span of w1 through wr because it can be written as a linear combination of those vectors. Similarly, if I take the vector u, for example, and multiply it by any other scalar k, then I get something else that resembles a linear combination. Or I shouldn't say resembles, it is a linear combination of the vectors w1 through wr. So this ku would also belong to the span of those R vectors, and that gives us closure under both of our operations. So there's your proof that this is a subspace. Okay. Now, oops, it's upside down. Flip that guy around. There we go. All right. So for part B, to show that the span of those R vectors is the smallest subspace containing those R vectors, we're going to let W be any other subspace of V that contains those vectors, W1 through WR. Now, what we want to do is show that the span of those vectors, W1 through WR, is in fact a subset of W. And remember, the way that we show that something is a subset is we show that for any vector that we could pick in this set here, that vector also needs to belong to this set here. That would show that this is a subset of this, or subspace, since they're both vector spaces in their own right. So let's pick an arbitrary vector v in the span of those R vectors, and by choosing that v from this span, that means that v can be written as a linear combination of those R vectors, k1, w1, and so on. Now, w not only contains those vectors, but we're also assuming that it's a subspace. So it has all of the axioms that you would expect from a vector space, namely closure under both operations. So because it's closed under scalar multiplication, first of all, the fact that those R vectors belong to W means that for any scalars, k1 through, for any scalars, but in particular k1 through kr, we have k1w1 and k2w2 and all of the others through krwr belonging to that subspace. That's closure under scalar multiplication that says that that has to be true. But then if these R vectors that I'm listing here belong to our subspace, the fact that we have closure under addition as well means the sum of those has to belong to our subspace. But that sum, k1w1 plus k2w2 and so on, that's the same linear combination that gave us v. So if that belongs to w, then that means v is in w as well. There's where we get our subset. Okay? So that proves that first theorem. Let's run through a couple of examples here, starting with this one. Let's let this 2x2 matrix A, B, C, D just be any arbitrary 2x2 matrix in the vector space M22. Then notice we could decompose. Remember how I said that decomposition is that common theme in higher math. I can decompose this into a linear combination of simpler matrices by writing it this way. Notice each of these matrices has a 1 in one entry and zeros elsewhere. So a 1 here, 1 here, 1 here, and 1 here. And I pulled the scalars that I was having as entries here out, so that what I have is a linear combination of these four matrices. So what that means, because this vector was chosen arbitrarily, meaning, I said vector, but matrix, in this context it's a vector in a vector space. This matrix can be written as a linear combination of those four matrices, and that would be true of any matrix in M22. Then that means that that set of matrices that we have here would span M22. Okay, that's what that means by definition. In fact, this particular set we call the standard basis for M22, and we'll give more meaning to that term later. Okay, let's take a look at another one. This is a different set, and we want to determine whether or not this set spans M22 as well. And if it does, we want to express this specific matrix in M22 as a linear combination of these four vectors. If this spans all of M22, then this has to be possible, because that would mean that all vectors in M22, all matrices in M22, can be represented as a linear combination of those four. So how do we do this? Well, similar to what we did here, we're going to let A, B, C, D be some arbitrary matrix that we've chosen from our vector space. M22, and try to form some linear combination that makes that. So I'm going to use k's for the constants here. K1 times the vector or the matrix 2, 0, 0, 0 plus K2 times the next matrix 0, 0, 1, 1 plus K3 times the next one 0, 4, 0, 0 plus K4 times the next one 1, 1, 0, 0, and I want that to equal the arbitrary matrix A, B, C, D. Okay, so basically if I can find scalars K1 through K4 such that when put into this linear combination here can generate this matrix regardless of what this matrix is, then I will have shown that this is a spanning set for M22. Now, in order to do this, what I want to do is turn this into a system of linear equations. So if I focus on just the first entry here, notice the first entry here after multiplying the K1 in is going to be 2K1. And then I'm going to add to that a 0. And then I'm going to add to that another 0. And then multiplying this K4 in, I'm going to have plus K4, and that's going to equal the first entry here, A. That's where that A should come from, just those first entries. If I do this for the remaining entries, so for example, I'm going to have a 0, a K2 here, a 0, and a K4 there. That should equal the first row, second column entry, B. And then down here, I have a 0 plus 0 plus 4, 4K3, so 4K3, okay, plus 0 again, so there's actually no need for the plus there, that would equal C. And then looking at my fourth entry, I'm going to have 0 plus K2, so I have a K2 here, 0 and 0, and that's going to equal D. All right, so I'm going to say D. Let's turn this into an augmented matrix. Okay, so this looks like the matrix 2, 0, 0, 1. And then I have an A here, 0, 1, 0, 1. And then 0, 0, 4, 0. And then 0, 1, 0, 0, and then I forgot my B, C, and D. Let's double check, make sure we got that right. I think that's right. Yep. Okay. So now, do I need to explicitly solve for K1 through K4? Well, no, I don't actually need to do that explicitly, because the goal is just to show that this is consistent for every choice of A, B, C, D. But remember, we have that equivalence theorem that gives us a lot of nice tools for verifying that. So how do we show that this is consistent for every vector A, B, C, D from R4? Well, all we need to show actually is that this matrix here is invertible. That's from our equivalence theorem. Those two statements are equivalent. So to show that this is invertible, I have different ways of doing that, but probably the easiest way is to evaluate its determinant. Now, the determinant of this matrix, so just like this, 1, 0, 1, 0, 0, 4, 0, and 0, 1, 0, 0. It doesn't matter what the determinant is exactly equal to, as long as it's non-zero. That's all we need for this to be invertible. Now, I'll let you compute the determinant yourself. It's a very easy one to do, even though it's a 4x4. Notice you can do row reduction, and if you just do -1 times row 2 plus row 4, you'll put this thing in row echelon form. This will become a 0 here, and then you can just multiply the diagonal entries. But this will not equal 0, which means that this is invertible, which means that this is consistent for every choice of A, B, C, D, which means we always have a linear combination that will give us this, which means this is a spanning set for M22. So S spans M22. Okay? Now, I'm running out of time in this video, so I'm going to do the rest of this in the next one. But let me just illustrate what we're going to do to get us started in the next video. Now that we've shown that this set spans all of M22, the goal is to show or to come up with a specific set of constants, K1, K2, K3, and K4, that we could put in here such that this linear combination comes out to that matrix, 1, 2, 3, 4. And in order to do that, all we'd have to do is go to this augmented matrix and replace the A, B, C, D with 1, 2, 3, 4, and then actually solve this using Gauss-Jordan elimination and call it a day from there. Okay, so we'll do that in the next video.